All right, let me give you an example. You sure you understood this, right? Kapıyı rica edeyim ben. Kapıyı kapatır mısın? Okay, so let me give you an example. And then I'm going to do an example on the computer. Okay. Right. So, rather simple numeric example. Given the following. It's a really simple one. Design an LQR controller. An LQR controller for comparable equal weights in the states and controls. So we want to have them comparable, so they will be approximately equal. Design an LQR controller for comparable weights in the states and the controls. Well, first write the LTI system. Write the LTI system. It will look like that. It's a two-dimensional system. 0, 1, 0, 0. x1, x2 plus 0, 1. Okay, that's that. So this one's A matrix. This one's the B matrix. So we are going to set up now the LQR problem. Look like this. J is 1 over 2. So infinity x1 x2 F matrix x1 x2 plus U G U dt. And we are going to choose 5 numbers now. And the problem is going to minimize J, the cost function. Okay? So, since they are going to be comparable, they are going to be all equal, what do you suggest? Let me make a suggestion. Since they're all going to be equal and comparable, let's put zeros over here again. and put 1s over here and the 1 over here. So it will be, what will be the result? It will be x1 square plus x2 square plus u square. Right? This will now be like this. J is equal to 1 over 2, 0 to infinity, x1 square plus x2 square plus u square. So as far as the optimization problem is concerned, it will try to, they will all have the equal weight. So it will try, reducing u is just as good as reducing x2 as just as reducing x1. So they will be all try to do, reduce them equally much, let's say. Okay, so I just put 1s. So you could put something over here in the upper and lower triangle, but what's going to happen is that then you will have x1 times x2 times 0. Do you want that? You can if you know what you're doing. Right? I mean, I'm just saying if you don't put a 0 here, you might have, let's say, if you put a 1 over here, what do you get? You'll get x2 times x1, right? x2 times x1. Does it help you? Probably not too much. Okay? But there might be situations where this might mean something, and then you might want to have it in your equations. I mean, in your weighting matrices. But this is typically what I would do. Does that make sense? Okay, so let's say I choose this. Now this is F now, and this is G. So if I had MATLAB, all I need to do is write these numbers over here, write LQR, and say K is equal to this, and boom, you have the result. But let me just show you what it looks like if you don't use your computer. The first thing you need to do is now, you know G, you just take the inverse. You know B, right? You don't know S, so all you need to do is find S. In order to find S, you need to solve this equation. And that's what we are trying to do now, try to solve the algebraic Riccati equation. So 0, 0, 0, 0, because it's a four-dimensional thing, times S1, 1, S1, 2, S2, 1, S2, 2, times A matrix, 0, 1, 0, 0, plus A transpose, zero, 1, 0, A transpose, plus S, S11, S12, S21, S22, minus S, like this, minus S11, S12, S21, S22, times B, times G over minus 1. G is 1, over minus 1 is again 1. And then B transpose, so 0, 1. And then S. Plus 1, 0, 0, 1. Okay. Is this solvable? You need to find four numbers, S11, S12, S21, and S22. Are they solvable? Do you have four equations from this? Yes, of course you have four equations, right? You do one equation and then you set it equal to 0, so you have four equations and four unknowns. So this should be solvable. So that's why it's called an algebraic Riccati equation, right? It's algebraically solvable. You understand how it's solvable? 4 unknowns, but you have 4 equations for each variable. So let me write down. Try to do this part here. You'll get 0 S11, 0 S12, plus 0, 0 S11, S12, minus 2 square S12, S22, S12, S22 square. Finally, you have minus S12 square plus 1, S11 minus S22. And you have these 4 equations now. S12 square plus 1 is equal to 0. S11 minus S12 is equal to 0. S11 minus So you can see that these 2 are equal anyway. So they are 2 equations. So you have multiple solutions because they are equal. And from this, you can find the following. S, a solution is this. S is equal to 3, 1, 1, 3. Okay. So that's your S. So calculate K from this. So K is equal to G over minus 1 B transpose times S. K would be equal to 1 times 0, 1 times S. And that's your feedback gain. So what it means is that you would simply have this U start is equal to AX plus BU. The way we had over there, output is X. You take X1, multiply it with 1. You take X2, multiply it with square root of 3. And you could have an extra control V, but this is of course for V is equal to 0, it will try to minimize everything. So these are your feedback gains. And these are our optimal feedback gains, right? They are optimal. Optimal feedback. Or we call them LQR gains. But you have some sort of an optimization here. Yes?
There's an S1 to square 1 plus 1 equals to 0, right?
Yeah.
It means that S1 to B minus 1 plus 1. We define S as a positive definite match, but S1 to not necessarily to become 1 minus 1.
So it could also be minus 1, you mean? Okay. Well, I didn't do the calculation here now, but it is either that it is not a positive definite matrix or it doesn't match over here. I have to check. I mean, any solution that's a positive definite matrix and that solves these 4 equations is a solution. I just chose one of the solutions, I guess. You have to go through this. Okay. But I can see this is a positive definite matrix right here because everything is positive, right? So naturally I would select this. So this is your optimal feedback gain. Now the question is, where did the eigenvalues move? I mean, we didn't really choose any eigenvalues. We don't have any desired eigenvalues. Where did the eigenvalues move? Now we can check this, of course. We need to look at the eigenvalues of A minus bk. Right? We just look at the eigenvalues of A minus bk. Where did the eigenvalues go? Okay. And that's quite straightforward. Let's look at, to look at the eigenvalues of A minus bk. Okay, so A is 0, 1, 0, 0, minus B, 0, 1, times K. 1, and that is equal to 0, 1, minus 1, minus square root of 3. We're going to look at the determinant of 0 minus lambda, 1 minus 1 minus lambda, 3 minus lambda equal to 0. And that will give you lambda square plus down 3 lambda plus 1 is equal to 0. And I don't really have the solution for this. From here you will get lambda 1 is equal to something and lambda 2 is equal to something, and that will be your lambda. Yeah.
Why do we have plus on the block diagram?
I wanted to add them together and then take a minus, but you're right, it's a minus minus. Thank you. Is that okay? Any questions? So let me show you how you do this in MATLAB. Okay, real quick. Oops. And on Wednesday, we will have this class where I do recitation, and I will do a lot of these LQRs on MATLAB and do a lot of these integral controllers and tracking and stabilization and so on and so forth. Here's an interesting, oh, this looks horrible. How are we going to do this? Can you see it? This is really tiny. It's really bad. I don't know how to. I don't think we can change it. Unless someone comes up there and changes it. Well, anyway. Before I go any further, I just wanted to remind you that I think I did this, right? Let's say I have this. Then I have x, and then I have this k plus minus v. So this would be a stabilization problem. We stabilize the system, and you have a operator on the side, and this is trying to stabilize the system. Moving this k over here, which makes it a tracking problem now. Plus bu x. These two architectures, the calculation of k is the same, right? Remember that. Because the system matrix for both cases is still a minus bk. So putting the k over here or here doesn't really change the problem. So in other words, if you want to find this k, it is still the LQR problem. It's the same way you calculate this k. The difference here is that here in this k, you're more trying to stabilize this k, whereas here you're trying to follow this v. If you look at this, if v is equal to x, then the output is equal to 0, which means it stay where you are. But if x is different from the command, then you have some sort of an input. The difference between this is, of course, that x and v has to match in size if you want to have a tracking problem. And here, x and v don't have to match in size. In fact, k can be anything. I think I've talked about this a few weeks back, but I will talk about this more on Wednesday, because this is now the practical application of how we apply this k. This would be a tracking problem where I try to track a certain velocity or a position, or here I'm just trying to stabilize the system. Okay, it's a little bit different. Okay, so first of all, what I wanted to show you is, just wait. First, I wanted to show you this. I don't know if you can see this, but this is from Bernard Atkins' book in the 96th edition. This is the linear A matrix and the B matrix for the longitudinal dynamics of an aircraft. And look at what you need in order to calculate the A matrix and the B matrix. I mean, I always give it to you, but how do you calculate it for an aircraft? You see that you have the aerodynamic derivatives, del x del u divided by m. You see the first variable? The first element over there? Del x del u divided by m. So in order to calculate the first number on the A matrix, which is a 4 by 4, is that you need to calculate del x, del u, and you need to know m. Okay? So this is an aerodynamic derivative. Basically, it says how much does the force change if you change u on the aircraft, right? If you keep everything else constant. So how do you calculate that? Well, the way you calculate this, you do it through wind tunnel testing, or you do CFD analysis, or you do flight testing, or you just look at similar airplanes and say an airplane has this del x, del u, and my airplane looks awfully similar, so it must be similar, and you choose that number. Okay? And you use that. You look at the second one, it's del x, del w. Right? That's the angle of attack. And what else do you have? You have a lot of stuff related to inertia, 1 over Iy and all that. So, first of all, in order to get the A and B matrices, you need to have the aerodynamic derivatives. And that is where all the aerospace engineering knowledge goes in order to estimate them properly. Okay? When you have an aircraft that already flies, that is one way. But oftentimes when you design an airplane, you don't fly it. You haven't flown it yet, let's just say. And then you still need those numbers. And then all these estimations and testing and all that stuff becomes quite important. So I just wanted to remind you that you still need the aerodynamic derivatives, mass and inertia terms in order to calculate the A and B matrices. So without those, and this is for the lateral, without those you can't even start to design a controller. Understood that? Okay. So, just wanted to quickly remind you on that because sometimes we forget where these things are really coming from. And of course, that's why you need a wind tunnel, right? So, help LQR. Boom. So, I really apologize, you can't really see this very well. So LQR is the command. I know you can see it very well. I just wrote LQR, help LQR, that's the command. LQR, linear quadratic regulator designed for state space systems. That's what we have. Okay? K, S, and E. LQR, system QNR, and all that stuff. Calculates the optimal gain K. For a continuous time state space model, the state feedback law is equal to U equals minus k times x, minimizes the cost function. J is equal to integral x transpose qx plus u transpose ru plus the cross terms x prime x transpose nu. So n we usually use 0 in our problem. We just have this q and r. I called them g and f. The problem calls it, MATLAB calls them q and r. Subject to the system dynamics, x dot is equal to ax plus bu. Okay, so that's our problem with n is equal to 0. That is exactly our problem. For discrete blah 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 blah, it gives you all that. LQR, this is another one, is an equivalent syntax for continuous time models. We have continuous times models with dynamics x dot equals ax plus bu. LQR is equal to a, b, q and r. Q and R is basically G and F, and N. N is equal to 0 in our case. That is basically this cross-producting thing, right? It's equal to 0, and that is equal to dx AX, and it will give you K, S, and E. So what are they? K is the feedback gain K. The matrix N is set to 0 when omitted. Also returned are the solution of S of the associated algebraic Riccati equation. So it will give you the solution of S of the associated algebraic Riccati equation and the closed loop eigenvalues A minus BK. Okay? So it will return you three things. After you set in A, B, G, F, and 0, it will return you three things. It will return you the feedback gain K. It will return you the solution of the algebraic Riccati equation S, and it will return to you the eigenvalues of the closed loop system A minus BK the one that I was just trying to calculate over here. Okay? So which is just one shot. So this is kind of the syntax that this thing has. So I would love to give you an example. I just need to set it up. I haven't really done this in quite some time. So just to be quick, maybe I can get one of the earlier examples that I did. Okay, I think I have something here. Just trying to see if I can. Let me see what I have now. Okay, that doesn't work. Maybe this one? Okay, so that's my A, that's my B. This is my R, this is my Q, 2, 3, 4, and I have an N. Good. So I think this was the example I did for the lateral dynamics of the aircraft. As I said, for Wednesday, I will try to okay, good. At least I have an example. For Wednesday, I will try to design you some examples, so it will look a lot better. But let me just, just for today, just to finish off and give you an example. So this was the lateral dynamics that we use for an airplane. Okay, and this is what you did in your homework, and that it's a 4x4, right? And that was the B matrix, right? That we use for this one control. So since we have 4 states, I'm going to use a F matrix that's going to be, again, a 4x4. And this is the F matrix that I have used in the past. 3, 1, 10, and 5. And I have zeros everywhere else. Okay, and the diagonal is 3, 1, 10, and 5. I believe one of these is the angular rate. This is probably the angular position. And this is the velocity and all that. So I made them 3 times. 5 times faster. So this is 10. And for the control, I have 5, somewhat comparable to the angle, I believe. And given this Q and R's, if I would choose this syntax, LQR is equal to A, B, Q, R, and N. Oh, N. N is equal to 0 because I don't want that cross product. Remember? So, and if I say LQR, A, B, Q, and R, N, I should get the K, feedback gain K, the algebraic Riccati solution S, and the closed-loop eigenvalues. Boom, and that's your result. So, K is that? 0.6 minus 28, 121 minus 12. That is your optimal solution of your K matrix, or here it's a vector. S, this is the matrix, solution of the algebraic Riccati equation, and the eigenvalues, they moved over here. Minus 12, minus 0.2, minus 0.2. So that's where it moved. I have no control over this. However, look at this. Let's say I take the Q take the Q. Instead of having 10 over here or 3 over here, let's make this 30. So I changed something here over here, okay? Let's make, instead of 3, I made the first variable here 30, okay? And I choose LQR, boom, you have the feedback gain K, which has changed now. Now this is 433. And look where the eigenvalues moved. One moved to minus 52 and minus 10. But now you have to understand kind of what is happening and which one is moving where. And this requires a lot of analysis and understanding of flight mechanics to have at least a clue what am I doing when I change the 3 to a 30. Okay? So, for instance, if I would change the 3 to 0.3, right? So this would be that. Or maybe I can choose also change the R from a 5 to a 1, which means the controls are not important anymore, or less important. And I can look at the LQR solution, and you can immediately see the eigenvalues moved a little bit more closer to the origin, and the feedback gain case did become a little smaller. Now, what would be nice is that to put this into Simulink and look at the response. Give a step input in Simulink and see how it works with this different case. And that's exactly what I want to do on Wednesday. Try different LQR solutions, give inputs, step inputs, and see how the aircraft moves with those feedback gains. Okay? And you can try this at home as well, of course. Try different LQRs and all this. And if you get confused how to use this syntax, as I said, say help LQR, and it gives you all these things. Okay? So see you on Wednesday, 11:40. Right? It's 11:40. Okay.